Hello physics students, and welcome to our second video in the topic, the electrostatics of point charges. So in the last video, I gave a brief synopsis of the topic, and I just want to remind you that the electrostatics of point charges, we're talking about the physics of things like protons and electrons, things that have just one tiny bit of charge in one location interacting with other similar charges. I also said in the last video that in this topic we're laying the groundwork for about half the course. The groundwork is four main ideas that are going to repeat themselves throughout the half of the course. One is electrostatic force. The second is electric field. The third is electrical potential energy, and the fourth is electric potential or voltage. Four ideas, and in the last video we concentrated on the first force, okay, force between two charges. And so we learned that plus plus repel, minus minus repel, plus and minus attract each other, and the amount of those forces, the strength of those forces is given by Coulomb's law, F equals K, Q1, Q2 over R squared, Coulomb's law. And then you could calculate the newtons, the force magnitude between the two charges. But yesterday, we confined our analysis to one dimension, charges laid across one line. Today, we're going to expand to the electrostatic force in two dimensions. And what I'm going to do is just do a couple examples to show you the techniques involved here. The first example, what we want to do is determine the net force on the 6 microcoulomb charge. So what I have here is a 4 microcoulomb and a 2 microcoulomb and a 6 microcoulomb, 0.2 meters away, 0.1 meters away, and we're looking for the net force on this charge right here, caused by the other two. So let me pause and give you an opportunity to jot this down. Okay, so let's begin our analysis. So first thing, this 2 microcoulomb is positive. This is positive. It's going to repel this 6. Repel means push it down. So what I'm going to do is draw an arrow in the downward direction. And since it comes from the 2 microcoulomb, I'm going to label it F subscript 2. Now, again, Newton's third law applies here. So since this top charge, the 2 pushes the 6 down, the 6 pushes the 2 up with exactly the same number of newtons. But I'm not going to draw that arrow because I don't want to complicate the diagram. We're just looking at the net force here. But just I want to remind you Newton's third law still applies. Okay, so now, in addition, we have this 4 microcoulomb charge, positive, positive, it's going to repel this way. So I'm going to draw that force. We're actually going to see later that it's less, a smaller number of newtons than the other force. So I'll draw it a little shorter. And just like this was F2 because of the 2, I'm going to call this one F4 because it came from the 4 microcoulomb charge. Okay. Now, this is obviously going to go somewhere along the diagonal because it's being pushed right and down at the same time. Exactly where? Well, what we do is we add these forces by creating a parallelogram, which in this case is going to turn out to be a rectangle. I make a dotted line here parallel with the 2, F2, and then horizontally parallel with this I make another dotted line. And where those two intersect, that's where the net force will end up. So I'll label this F net. And it's at a certain angle, theta. So I'll put a theta there. So to find that net force, what I'm going to have to do is obviously find these two forces first. So what I'm going to do before I do that is pause to give you a chance to catch up with the diagram. Okay, so I'm going to create a little bit more space here. And I will begin with the F4. I'm just going to check and see if we could see that well. Okay, it looks good. All right, so K, I'm going to use 9.0 times 10 to the 9th Newton meters squared over coulombs squared. You can use 8.99 if you want a little bit better precision, but 9.0 works fine and gets you full credit. And then the 4 microcoulomb charge is 4 times 10 to the minus 6 coulombs. That's what micro means. We got to plug in the coulomb value. And then we have the 6 microcoulomb charge, which is 6 times 10 to the minus 6 coulombs. And the distance between those two charges, 0.2 meters. So I plug that in, 0.2 meters squared. And that comes out, I believe, to 5.4 newtons. Okay, so that's the length of that arrow. What I'm going to do is find the length of the green arrow here. In other words, F2. Again, using Coulomb's law. Okay, plugging in the values. And 2 microcoulombs. And 6 microcoulombs. And the distance between those two charges, the 2 and the 6, is 0.1 meters. So I do 0.1 meters squared. If you run that through on your calculator, you get 10.8 newtons. So I have the Newton values of those two forces. One possible way to write this is in component form. Okay, so I could now say, if I wanted to, I have in the x direction 5.4 newtons to the right, so we put that as to the right positive. If it were to the left, we would put a minus sign. But to the right, it's along the x-axis, we could say 5.4 newtons I hat. Okay, that means 5.4 newtons in the positive x direction. And then this is in the downward direction. Well, this is positive y, that's negative y. So what I'm going to do is say minus 10.8 newtons j hat. Technically, that is a correct answer. So if they didn't say to specify how many newtons the net resultant force was, that is 100% correct. Now, of course, if they wanted to know the magnitude and the direction, then what I would have to do is use the Pythagorean theorem. Oops, I forgot. F4 equals and F2 equals. Okay, so if you haven't written this down yet, I'm going to pause the video here to give you a chance to catch up. Okay, So again, I'm now going to find this hypotenuse and angle just using some basic trig rules, obviously the Pythagorean theorem. To speed it along, I'm not going to write the equation out. I'm just going to say F net squared equals the, well, both the legs, the 5.4 in the x direction plus the 10.8 newtons in the y direction. Square those out, add them up, take the square root of both sides, and I believe you get 12.1 newtons. So there's the magnitude of the net force of those components. And then the angle, well, I could use the tangent function. Tan theta is the opposite side over the adjacent. I have a right triangle right here. Of course, if this is 10.8, so is this. So we got 10.8 over here and 5.4 over there. So when I say tan theta opposite over adjacent, I'm going to have the 10.8 divided by the 5.4. The Newton unit goes away, and that's exactly 2.0. So theta is the inverse tan of 2.0. And if you hit that on your calculator, I believe you get 63.4 degrees. So that is the equivalent of this, but with magnitude and direction under the x-axis. Okay? So if you haven't already done so, I'll pause a minute to allow you to copy this down. Okay. Second example for today. Y equals. Okay, so okay, so these are the charges, how they're laid out. And I'll pause a minute to allow you to catch up. Okay, so we're looking at trying to find the net force on this charge. All the charges are positive, but they're positive to Q, Q being some, variable. So What we have to do is find the force from this charge and that charge and then add up and find the net force. So since this is positive, it's going to repel this charge away. And here's the direction. Okay, so it's going to repel it in that direction. I'm going to draw an arrow up like this. Yeah, I guess I could call that F1. And then this plus 2q charge is also going to repel this up in this direction. So this charge repels like so. Now it turns out that those are actually equal length arrows. Okay. All right. So what'll happen is when these add up, the horizontal components here are going to cancel, right? I could think of this blue arrow as, and I'm going to erase these in a second, but it goes up like this with the force and over like this. And this force here has an upward component and a horizontal component. So obviously, if this is the same length and they're at the same angles, this number of newtons and this number of newtons cancel each other, the left and rights. And all that's going to be left is the upward net force, which these two then add up to a net force. Something like this, straight up. All right, so the first thing I have to do to find that is I need to find the lengths of these two arrows. As I said, they're the same length. Okay, actually, I forgot. Let's pause to allow you to catch up with these arrows. Okay, so what's the length of one of these arrows? So taking this F1, I have 2q and 2q, those are the two charges, divided by r squared. Well, how far apart are these charges? Not A, not 2A, but the hypotenuse of those two lengths, right? A, 2A, I need this distance. So r squared is this squared plus that squared. So I could write and that's what r squared is. So in the top I have 4kq squared. And in the bottom here, I have to square everything in the parentheses. This is actually 4a squared right here. Plus 1a squared gives me 5a squared. Okay, so I have the length of these two arrows. As I said now, what I have to do is find the vertical component of one of those arrows and then double it because I have one vertical component here and another vertical component here. I could express that like this. F net equals 2F in the y direction. And what's the y direction force? Well, if I put a theta here, this y direction is the adjacent side to the angle. So I could replace this with 2F cosine theta. All right, and that'll give me F cos theta gives me the adjacent side. I double it because there are two of those. Let me fill in the pieces now. So, 2, F is there. Okay. And a lot of people would be tempted to just write cos theta here. But here's a little trick. This is going to come up all throughout the year, this little trick. This theta right here is the same as this theta. And if I just redraw that triangle, I've got 2a here, a here, and this hypotenuse squared is 5a squared. So this hypotenuse is actually radical 5a, the square root of 5a squared, right? A squared plus b squared equals c squared. So c is the square root of this. And so the cosine, looking at this triangle right here, is the adjacent side over the hypotenuse. So that's this I could even do, yeah, that's good. A over radical 5a. So this is cosine right here. Okay. The a's over here cancel, giving me an extra radical 5, and so finally I could write F net equals 8. A's gone over there, right? And so what's left in the bottom is 5 radical 5 a squared. Okay, let me pause a minute to allow you to catch up jotting that down. Okay, just one little quick point. Some people might be tempted to rationalize the denominator here by multiplying top and bottom by radical 5. You're welcome to do that. I don't think in the AP they take points off for not rationalizing the denominator. I've never seen that. So you could leave it like that. You're welcome to leave it, even though in math class they would want you to fix that up. So that's it. That little trick, when you go back to the diagram for the cosine or the sine of something by looking back at the dimensions given, as I said, will appear throughout the year. But I just want to again summarize today we were out of the 4 ideas: force, electric field, electric potential energy, and electric potential or voltage. We concentrated on the force again in this video, and we expanded our analysis into 2 dimensions. What that might mean is that you use the Pythagorean theorem if the forces are 90 degrees to each other and tangent function, or in cases like this, you have to possibly pick a trig function to pick a particular component. Some of the components cancel, and then we just added the forces by doubling the y components here, because there are 2 of them. So that's the technique we use. But any kind of trigonometric analysis, you might use the law of cosines in an analysis to find the net force. So that's it. Just find the pieces using Coulomb's law, KQ1, Q2 over R squared. You find the individual forces, then you use some kind of math operation to get the net force. Okay, so that's it for today. I will see you in the next physics video.